Good evening and welcome to Perimeter Institute's public lecture series here in the Mike Lazaridis Theatre of Ideas in Waterloo, Ontario, Canada. My name is Heather Clark, Executive Director of Advancement here at Perimeter, and it is my sincere pleasure to welcome everyone here this evening, not only those of you who are in the theatre, but those also tuning in online. I would also like to take this opportunity to acknowledge BMO for Women as a supporting partner for tonight's lecture. Thank you very much, BMO, for your partnership. Tonight's lecture will last approximately 1 hour and will be followed by Q&A. For those of you who are watching online, we are fortunate to have Dr. Damien Pope, along with his team of PI researchers online and ready to answer any questions you may have throughout the lecture. Please use hashtag PI Live if you want to join that conversation. I will also accept questions from the hashtag PI Live Twitter feed during the Q&A. It is now my distinct pleasure to introduce you to tonight's speaker, Dr. Phiala Shanahan. Phiala Shanahan is an assistant professor of physics at MIT. Professor Shanahan grew up in Adelaide, Australia, and obtained both her Bachelor of Science and PhD from the University of Adelaide in 2012 and 2015, respectively. Before joining the MIT faculty, Professor Shanahan was a postdoctoral associate at MIT from 2015 to 17 and held a joint position as assistant professor at the College of William and Mary and senior staff scientist at the Thomas Jefferson National Accelerator Facility from 2017 to 18. Professor Shanahan has been honored by both the Australian Institute of Physics and the American Physical Society. She is a recipient of a career award from the National Science Foundation and was listed in Forbes magazine 30 Under 30 in Science in 2017. Phiala is currently visiting Perimeter Institute as part of our Emmy Noether Fellowship Program, a very important program that is rather dear to my heart that supports and encourages gender diversity in science. Please join me in a warm welcome to the stage, Dr. Phiala Shanahan.
Thank you very much. It's an absolute delight to be here today to talk about one of the fundamental, even defining questions for physics. What is everything made of? Debate about this topic, recorded debate, goes back to 500 or 600 years BC. And of course, scientific thought has progressed a lot since then, but trying to answer this question, what are the fundamental building blocks of the universe, is still driving the frontiers of physics forward today. We understand that matter is made of atoms. Atoms are inconceivably tiny. If you imagine walking along your favorite beach, there are more atoms in a single grain of sand than the number of grains of sand on that beach. Despite the name atom, which means indivisible, atoms have substructure. At their core is a densely packed nucleus of protons and neutrons orbited by a cloud of electrons. We understand that the structure of atoms actually goes one level deeper. Protons and neutrons themselves are made of more fundamental particles, matter particles called quarks, held glued tightly together by force-carrying particles that embody the strong nuclear force called gluons. As far as we know, that's it. There's no deeper levels of structure to be found. Quarks and gluons are fundamental building blocks of the universe. Of course, it would be a very exciting day for science if we found out that that's not the case. Quarks and gluons and their interactions are described by what's known as the standard model of particle physics, or the standard model of elementary particles. There are 17 fundamental particles, 6 different types or flavors of quarks called up, down, charm, strange, top and bottom. Particles called leptons, which include the electron and the electron neutrino, as well as heavier copies of those called the muon and the tau. 4 force-carrying particles, the gluon that we've already heard about for the strong interactions, the photon for electromagnetic interactions, and the W and Z bosons, which carry the weak force, and the Higgs boson. This theory was written down in the 1970s, but it wasn't until more recently that all of these particles were actually found experimentally in accelerators. The W and Z boson in 1983, the top quark in 1995, the tau neutrino, most recently in 2000, and then an event I'm sure many of you would remember, the Higgs boson, was the last piece of this puzzle to be found experimentally at the Large Hadron Collider in 2012. The Standard Model describes 3 of the 4 fundamental forces that we know of in nature. Electromagnetism, that's what binds the positively charged nucleus of an atom with the negatively charged electrons. The strong nuclear force, that's the force that overcomes the repulsion of 2 positively charged protons to bind them into an atomic nucleus. The weak nuclear force, which is responsible for beta decay, the conversion of a proton to a neutron, the decay of that proton. What's not included is gravity. Gravity is described by a different theory of general relativity, and trying to unite these 2 frameworks into one unified theory is still a grand challenge in physics. The equations that describe the Standard Model, these 17 fundamental particles and their interactions, are beautifully and wonderfully, alluringly concise. You can fit them on your coffee cup. Yet, to the best of our understanding, this theory describes the strong electromagnetic and weak interactions at all distance scales. From the internal dynamics of quarks and gluons in the inside of a proton, to the way protons and neutrons come together to form atomic nuclei and the elements in the periodic table, through to the nuclear reactions that happen in the burning of the sun, the conversion of hydrogen to helium that emits light that we see as sunlight here on Earth, to nuclear reactions that we see here on Earth, for example, to generate energy or for medicine. And even up to the cosmic scale, this theory describes the dynamics in the inside of a neutron star, the most densely packed objects in the universe that we know about. So I study the Standard Model of elementary particles, and there are really 2 motivations for this. First, I want to understand how the universe is built from these 17 fundamental building blocks, see the complexities of nuclear physics emerge from this theory. And secondly, we want to understand new physics beyond the Standard Model. But to do that, we need to know Standard Model backgrounds, benchmarks. We have to understand the Standard Model to find where it breaks down, to learn new things about the universe. Although the theory is so elegant, I still can't sit down and calculate something that I might like to know by hand from the Standard Model, let's say the mass of the proton. We just don't know how to do the maths, how to solve those equations. What we can do is to put the theory onto a computer. Essentially, we discretize the theory, put it onto a 4-dimensional space-time grid. That's 3 dimensions for space and 1 for time. And in that formulation, we can calculate things from the theory, like the mass of the proton, on a computer. Now, these computations are extraordinarily demanding. Some of the calculations that I'll discuss, if you were to put them on a fairly good laptop or desktop computer that you might have at home, would take 10,000 years to complete. Of course, that's not what we do. I use the most powerful supercomputers in the world. Just to give you an idea of the scale of this computation, the biggest supercomputer in the world at the moment is known as Summit. It's at Oak Ridge National Laboratory in the US. It's a physically large machine, here's a person for scale. And computationally, this machine is huge. The Summit supercomputer can do in 1 second what it would take the entire population of the world a year to do if everyone did 1 calculation every second for the entirety of that year. This is an enormous amount of computational power. And we can use that computational power to understand the universe from its fundamental building blocks. Starting at the smallest scales, the structure inside a proton. What we learn from the Standard Model is that the building blocks of the universe are not at all like Lego blocks. The simplest description of a proton has 3 quarks held glued tightly together by gluons. But what we see is that as you probe the structure of the proton at higher and higher energy scales, a more complicated dynamical structure emerges. Quark and antiquark pairs, antiquarks are the antimatter particles that correspond to quarks, can emerge out of empty space, out of what we call the quantum vacuum, and then annihilate again. And what you see is a bubbling, boiling, dynamical, complicated structure on the inside of the proton. But we can study this structure to understand some of the fundamental things about our universe. For example, we see in an experiment that the neutron is just ever so slightly heavier than the proton, by about 0.1%. That small difference is absolutely essential for life as we know it. The proton is the nucleus of the hydrogen atom, and it's that attraction between the positively charged proton and the negatively charged electrons that holds it together. If we were to suddenly reverse the mass difference of the proton and neutron, so the proton's now heavier, the proton could decay. Without those electrostatic forces to bind them, matter would collapse into black holes or into neutron stars. We wouldn't be here to ask these questions. What we can measure experimentally is that there is this very small mass difference between the proton and neutron. What we can do from the standard model is understand it in terms of the fundamental constituents. So this is very recent work. Just from the last few years, we were able to calculate the mass difference between the proton and neutron. The experimental number is shown here in orange, from the standard model, and see that this small difference arises from a delicate interplay of the strong and electromagnetic interactions, which push the mass difference in opposite directions and cancel to give us the same number that we observe in nature. So moving from the mass of the proton to another fundamental property about the proton, the pressure generated by the quarks and gluons inside. This is even more recent work. We only released this in the last month. We calculated the pressure distribution inside the proton. So in this figure, over on the left-hand side is close to the center of the proton, and as you move out, you're moving further out from the center towards the outside. We find a positive pressure in the inside, that's a repulsive pressure, and as you move further away, a negative, a confining pressure inside the proton. What's quite remarkable is that the pressure inside the proton at its peak value is greater than the inside of a neutron star, the most dense known objects in the universe. So unlike the proton-neutron mass difference, which we've measured extremely precisely experimentally, this is an example where theory is more precise than the current experiments. We have a prediction to be tested at future experiments. So there really is a synergy and an interplay between theory and experiment as we strive to learn more about the universe. And this is a particularly exciting time for thinking about the structure of the proton. In the next 10 years or so, we expect a new particle collider, an electron-ion collider, to be built in the United States. And this machine is designed precisely to study the internal dynamics inside a proton and will allow measurements of things like the pressure distribution to a much higher precision than we've ever had before. So we really are looking at a new frontier of understanding of the smallest things in the universe. So moving from the very small up to the more cosmic scale. As I said, we believe the standard model describes the strong electromagnetic and weak interactions at all distance scales. So they describe the primordial nuclear reactions that happen in the first moments after the Big Bang. After the Big Bang, the universe was a hot, dense particle soup. As the universe expanded and it cooled, within about the first second, we had protons, neutrons, electrons, photons, neutrinos, and their antiparticles. Then what happened is called Big Bang nucleosynthesis. In the 10 seconds to 20-minute time interval after the Big Bang, those first protons and neutrons combined in chain reactions that formed the very first elements. So here in the first step, protons and neutrons fuse into a deuteron, a two-body state, and then the chain reaction continues. So a few years ago, this first step of this first nuclear chain reaction was studied from the Standard Model for the first time. So we were able to really understand how this reaction emerges from those underlying quark and gluon degrees of freedom. And this was a really exciting achievement. This was the first study of a nuclear reaction from the same theory that describes the internal dynamics of a single proton so well. This is also important because in this reaction, the internal degrees of freedom are really important. It's one of the places where the fact that protons and neutrons have this substructure shows up strongly. So we were able to study this from the Standard Model for the first time. Moving to another important nuclear reaction, the reactions that power the sun. The light and heat we see from the sun comes from the proton-proton fusion chain reaction. Again, at the first stage, protons fuse, and we follow all the way from hydrogen down to helium. And the light emitted on the way of this chain reaction is the sunlight that comes down to us here on Earth. Just last year, we were able to study the first step, again, of this proton-proton fusion chain reaction from the Standard Model of elementary particles. So we really are just at the very beginning of an era of understanding nuclear physics from the ground up, understanding nuclear physics from the interactions of fundamental particles. As I hinted at the start of the talk, the Standard Model isn't everything. There are things about the universe that the Standard Model doesn't explain, but Standard Model calculations are essential for working out exactly what that new and unknown physics in the universe is. For example, gravity. That's described by a different theory, not by the Standard Model, and unifying those is a grand challenge. Neutrinos are massless in the Standard Model, but we see experimentally that neutrinos have mass. There are many theories, many proposed mechanisms for putting neutrino masses into the Standard Model, but working out which is the one that best describes our universe is still an open research question. There's also a matter-antimatter asymmetry in our universe that the Standard Model can't explain. If the Big Bang had produced equal amounts of matter and antimatter, and then all of the evolution had proceeded just by the Standard Model as we understand it, then there wouldn't be nearly as much matter left in the universe as there is. We are all made of matter. The stars and the planets that we see, that's all matter, not antimatter. The matter and antimatter would have annihilated and there'd be far less left by now. Also, dark matter, which I'll spend a lot of the rest of the talk discussing. By about 1980, it was clear that there's a fundamental problem in our understanding of the universe, that what we understand and what we measure from the universe don't match up. What I have here on the slide is a picture of the Coma cluster. This is a large cluster of galaxies near Earth. And as early as the 1930s, it was noticed that the gravitational attraction needed to hold this cluster together couldn't just come from the luminous matter, the matter that we see. There's not enough. But if there was some type of other matter, something that interacts gravitationally, but that we don't see, something that doesn't emit or absorb light, something dark matter, now that could explain this. Another observation was that the speed, the velocity with which the rotation of a galaxy happens isn't what we'd expect. If you look in this figure, as we move out from the center of the galaxy, the velocities that you expect, the galactic rotation curve from the matter you can see, follows this red line. What you actually observe, however, is quite different. It's like this white line. So again, there's something interacting gravitationally that we can't see. Just one more example. This is a now famous picture of what's known as the bullet cluster. What you see here, it's in false color, is pink areas which show matter that we can see, luminous matter. We see light or we see X-rays. That's matter we can see. And here in the blue, matter that we can infer is there. Matter that's interacting gravitationally, that we don't see. And you see there's a clear separation here. So we infer these blue areas using something known as gravitational lensing. That is, that light will bend around a massive object in its way. So if we're here on Earth, receiving light from a distant star, and there's something massive in between, light from that star will bend around that mass to reach us. What we then see, since all we see on Earth is the last direction that that light came from, is ghost images, virtual images of the star in the directions from which that light came. You can understand this by thinking about how a mirror works. If you're standing in front of a mirror and you're looking at your toes, what's happening is the light from your toes is bouncing to the mirror and to your eyes, and you see a virtual image of your toes on the other side of the mirror. So it's the same sort of virtual images of stars that we see. What I've shown here on the slide is just these two light rays either side, but you have to imagine this in 3 dimensions. So what you really see are rings. And that's exactly what you see. These are sometimes called Einstein rings. So using this, we can infer if there's mass that we can't see by the bending of light around it. And that's how these images were made. So the bullet cluster is just one example. There's a number of examples where we can see this separation of visible mass and inferred mass. So really, we've deduced the existence of dark matter by accumulating evidence, and dark matter is the best theory that fits the evidence. We've never seen it, we can't. It doesn't emit or absorb light, but we know it has to be there. So just an example of how the dark matter might explain this separation. Even in a simple model where we have 2 galaxies with the same distribution of visible matter and dark matter, and we bring those together, the visible matter, it interacts, it will collide. The dark matter will just sail right on by. And so you can see in this collision of 2 galaxies, even from this very simple starting point of the same distributions, can produce exactly the sort of images that we see by observing the universe. Not only can we infer that dark matter must be there, we can infer exactly how much of it there must be. And it turns out quite a lot, about 5 times as much as ordinary matter. Ordinary matter, that's the matter that makes up you, me, the stars, the planets, everything described by the standard model. Dark matter is about 5 times as much of this universe pie. The rest is dark energy that I won't say too much about, other than, again, we've inferred that dark energy must be there. There's a lot of mass in the universe that's interacting gravitationally. So the expansion of the universe over time should be slowing down, pulled back by that mass. But it's not. The expansion of the universe is accelerating. So dark energy is what we call something that has to be driving that acceleration. So back to dark matter. What do we know about dark matter? Well, of course, it interacts gravitationally. That's how we know it's there. It doesn't interact through electromagnetism, we'd be able to see it. It doesn't interact by the strong force, it doesn't seem to interact with cosmic rays, which are made of protons. Maybe, just maybe, it interacts through the weak nuclear force, which would give us a way to be able to see it and learn more about its properties. So we know really much more about what dark matter is not than about what it is. We know that it's not normal matter. It's not stars, it's not planets, it's not antimatter, it can't be galaxy-sized black holes because of the amount of gravitational lensing we see. And we have many, many theories for what dark matter could be. Maybe it has something to do with supersymmetry, or extra dimensions, or different force carriers, or different types of neutrinos. We have many theories, but we don't know which, if any, are right. All of these theories predict different properties for dark matter. So for example, here is the mass of a dark matter particle, and here is how strongly it interacts with normal matter. And you see that different theories for dark matter fill in different places in this model space. So how do we constrain that model space, rule out propose theories for dark matter or rule them in if we see a signal for dark matter. There's 3 different ways we approach this from experiment, using colliders and doing what we call direct detection and indirect detection. Here's a nice way of visualizing what those 3 different approaches mean. DM here in gold stands for dark matter, SM for standard model or your standard matter particles. Reading this figure from right to left, we have standard model particles collide to create dark matter. That's what we do at colliders. We smash regular matter, standard model particles together, and you hope that maybe you'll create dark matter. That would then escape from your detector, and you would know it's there from some missing energy or missing momentum from your detector. Indirect detection, reading the figure this way, you look out into the universe, and if somewhere in the universe dark matter is annihilating to create standard model particles that we can see, then you'd have an excess somewhere over what you expect, more standard model particles that you can't explain. And then you could deduce some of the properties of dark matter from that indirect detection. Direct detection, reading up or reading down, we build a detector here on Earth. A big vat of nuclei buried deep underground to protect it from other interactions, and you wait for dark matter to hit it. You look for a direct interaction of your dark matter particle with your normal matter. So in this way, we look for what are called WIMPs, weakly interacting massive particles, that will interact with a nucleus in our detector through the weak interaction. There are many limits on WIMPs from existing experiments. So this is the same sort of figure I showed before. Here's the particle mass on the horizontal axis, and here is how strongly that particle interacts with normal matter. Each of these lines comes from an experiment, and they're limits from experiments. Everything above the line, that part of the model space, is ruled out. So making this figure, however, ruling out those parts of the model space, ruling out models for dark matter, relies on theory calculations of how the dark matter would interact with the particles in your detector. Just the sort of calculations that I was describing before that can tell us about the internal dynamics of a proton, or about primordial nuclear reactions that power the sun or in the early universe. So understanding dark matter, again, relies on understanding the standard model. So all of these constraints at this stage assume that when dark matter comes in, it interacts with just a single proton or neutron inside the very large nucleus in your detector. And the interaction of dark matter with that single proton or neutron is something that we calculate using these big computational tools. Just this year, we've done some new calculations for the first time of how a wide class of dark matter particles would interact with multiple nucleons in your detector, multiple protons or neutrons at the same time. And what we found was that these multi-particle interactions are surprisingly large. That means that if we see dark matter at one of these experiments tomorrow, before we can really interpret what it is, we need to do a lot more work to understand the theory. So many dark matter experiments, most of them, use large nuclei. For example, xenon is a commonly used nucleus that has 130 protons and neutrons. So what you measure is how dark matter is interacting with a body made of 130 protons or neutrons. What you know from theory is how your model for dark matter interacts with one, or maybe with two. And we've just shown that the 2 and 3 body pieces are much larger than you'd expect. So going up to 130 is a huge extrapolation. So to really understand what dark matter is if we see it, we need to do much more intense computations again. So I've said that we're really at the beginning of an era of understanding nuclear physics from the standard model. we really are just at that beginning. Many of these problems that we'd like to solve, many of these questions that we'd like to answer, are still too expensive computationally, despite the fact that we have the biggest supercomputers in the world. For example, the structure and interactions of larger nuclei from the standard model. So far we've studied the one-body, two-body, three-body, four-body type systems. Dark matter, like I said, dark matter detectors use nuclei with 130 bodies. Neutrino nuclear scattering is an experimental tool that we can use to learn more about neutrinos. Like I said, neutrinos are massless in the standard model, but they have mass in nature. So we want to understand those masses. We want to understand the ordering of the masses of the different types of neutrino. Neutrino nuclear scattering experiments also use nuclei in the detector. For example, there's a big experimental program in the United States called DUNE, which uses argon. That's a nucleus made of 40 protons and neutrons in the detector. To use the results of that experiment to really understand neutrinos, we have to understand the nuclear physics of argon. Again, a very large nucleus. Double beta decay is another tool that we can use to try to learn more about neutrinos. Double beta decay is where two neutrons decay via beta decay to two protons at the same time. And studying this can teach us about neutrinos. But the lightest nuclei that undergo double beta decay are again quite large, with tens of nucleons. So studying this again directly from the standard model, as we need to do, is massively computationally challenging. There are even simpler questions still that are too difficult computationally for us to answer right now. And this one, this happened when I was in graduate school, and it's been something that's been of great interest to me ever since. In 2010, we realized that we don't really know the size of the proton. You'd think, like the proton mass, that its radius or the proton size would be something that we know extremely well. But for the last decade, there have been conflicting experimental results for the size of the proton. If you measure the size of the proton from a hydrogen atom, you get something quite different than if you measure the size of the proton using muonic hydrogen. That's a hydrogen atom where instead of an electron, you have its heavier cousin, the muon, in the atom. And that difference is really quite striking. Here you see results from muonic hydrogen. This is the proton radius on the horizontal axis. And over here, you see different experimental results using electronic hydrogen. The width of this band gives you an idea of the uncertainty on the results. And these two bands are very, very many bandwidths apart. Right? They're very different. Is this a sign of new physics? From the standard model, the proton radius should be the same thing no matter how you measure it. We don't know. To find out, what we really want to know is what is the radius of the proton from the standard model, from the fundamental quark and gluon degrees of freedom. And we can calculate that, but the error bar, how uncertain we are about the results, is far larger than the difference between these two experimental measurements. Doing better, being able to differentiate between these two, it will take far more computation than we have available at the moment. So all the way from these complicated nuclear physics questions to really fairly simple ones, like what's the size of the proton, we're still limited by computation. Computers improve, and they improve really, really quickly. It's called Moore's law, that computational power improves essentially exponentially. So for the last decades, every 2 or 3 years has seen a doubling in computational power. The different lines on this figure, this is the sum of the top 500 supercomputers in the world. This is the top 1. This is number 500. You can see all of them are improving exponentially quickly. On this axis, each line is 10 times better than the last line. But that's not enough. If I want to answer these questions in my lifetime, even this exponential increase in computer power won't be enough. So, the answer is, of course, to work smarter. Spend a lot of time working on new algorithms, new ways of putting the standard model onto the supercomputers so that we can do these calculations more efficiently with less computational resources. That goes from things like sparse matrix inversion, that's how you deal with matrices, very large arrays of numbers where very many of them are zero. Are there efficient ways of dealing with such matrices? To things like noise optimization. Is there a way of having calculations where each sample doesn't fluctuate as much, so you have a cleaner signal with fewer samples in a well-defined way? To just in the last few years, I've been exploring the applications of machine learning to these sorts of problems. Of course, machine learning has been wildly successful in domains like image recognition, the fact that Google can tell you if your photo is a dog or a cat. So I, of course, don't want to know if my photo is a dog or a cat. I want to study the standard model. And so adapting these sorts of new tools in machine learning and artificial intelligence to these precise physics questions and to the scale of these massive computations is a great task. There are also other opportunities like new options in computation, new computational paradigms like quantum computing, which is still in its very, very early days. But there's a hope that maybe a quantum computer, where instead of binary bits you have quantum bits storing information, will be exactly the right way to study these complicated quantum systems. So there are different ways to approach using quantum computation for these sorts of problems. The first is start from the ground up. Put your theory of the standard model onto a quantum computer, like we do on classical computers, and do the calculation. Now that is a long, long, long way away. At the moment, the quantum computers we have are small, they're noisy, and putting even simpler theories on them is still a challenge. Another opportunity that I'm exploring is with these first quantum computers, these small, noisy quantum computers, are there parts of my calculation, maybe just a piece, that you could outsource more efficiently to a quantum device? So rather than trying to do the whole calculation from the ground up in a quantum framework, are there just pieces that might accelerate you enough to get over the hump to studying something like complicated nuclear physics from the standard model? Another really exciting opportunity is given by FPGAs, that's field programmable gate array hardware. These are new types of computer chips. And what they allow, as the name suggests, is for you to basically reprogram, reconfigure the chip after it's been produced. That gives us an opportunity to radically tailor a computer to the calculations that you're trying to do. So for example, the calculation of the proton radius. Much like you might build an experiment to measure the proton radius, I want to build a computer to measure, to calculate the proton radius from the standard model. A computer so radically tailored in the hardware and in the geometry of its connections to be exactly what I need for this theory calculation, that I can do something that on the biggest supercomputers in the world now, which are generic computers, they're used not just for my calculations, but for all sorts of scientific applications, do something that they couldn't do in the next 50 years. So by doing this, I hope that we might be able to answer some of these questions. For example, what is the proton radius from the standard model in the next 5 or 10 years? So with that glimpse towards the future, I want to leave with this picture. So the standard model that I've described, it's been an extraordinarily successful theory of the universe. For the last 50 years, this theory has withstood almost every test that we've thrown at it, other than the ones that I mentioned, right? So over that time, we've found that this wonderfully elegant theory describes everything from the internal dynamics of a proton. It can explain why the neutron is heavier than the proton, and through that, why atoms don't just collapse in on themselves if the proton could decay. It can explain the first steps of the first ever nuclear reactions in the moments after the Big Bang. And of course, we want to explain the next steps too from the theory, and that will require more computation again. The Standard Model can explain the chain reactions that power the sun, that give us light and heat here on Earth. And ultimately, what we want to see is, can this theory explain all of nuclear physics? Can we get the periodic table from the Standard Model? And hopefully we can't. Hopefully we'll find places where the theory breaks down that point us again in the right direction, like gravitational interactions not working quite as we expect points us in the direction of dark matter. Hopefully we'll find something that points us towards the new and unknown physics in the universe so that we can build a new Standard Model to understand even more of the universe's structure. Thank you.
So, we've got time for questions and answers. There is a microphone right here, and if people just want to come over to the side. And we've also got some online questions.
Thanks for a really great talk. I appreciate that. My question is about dark matter. Is it possible to take the piece parts from the Standard Model with a cookbook, put them all together, and in fact come up with something which meets all the criteria, i.e., no electromagnetic interaction, totally neutral, fairly large, that sort of thing? You know what I mean? Or do you need something totally and completely new?
We need something totally and completely new. Yeah.
Hi. Could dark matter possibly be responsible for the asymmetry between the ordinary matter and antimatter?
Yeah, so that's a really good question. Of course, it depends on exactly what dark matter ends up being. And there are, with most theories, no, probably not, but then most theories for dark matter are really quite simple. We say, well, what if dark matter is this particle? But we know that normal matter is extremely complicated. We have these 17 fundamental particles and all of these complicated dynamics that give us nuclear physics, and then we say, well, 5 times as much matter that's dark matter, that's just going to be one thing. Right? So our understanding of dark matter is so limited that it's really hard to answer that question. But that would be great. If someone has a theory that explains dark matter and the asymmetry of the universe at the same time, that would be a great contender for a new theory of the universe.
Thank you.
Leigh Schmittner, before the war, discovered fission. She didn't really believe there was a phenomenon. It was something as a surprise. After the war, obviously it's developed. Do we think we can engineer exotic forms of matter from the new elements we're discovering that might be the solution for the environmental crisis in the future?
So do you mean new forms of Standard Model matter?
That fission and fusion were a quantum leap to the energy we use today, even though it isn't enough. Can we discover a new level of energy from gluons and quarks and dark matter?
Yeah, so that's a good question as well. I guess the answer is, again, if you think about the fact that we've found ever deeper levels of structure. It's hard to say from the standard model that we know now how that might happen. But what if quarks aren't fundamental particles? What if there's another level of structure again? What if there's a whole level of structure beyond what we currently understand? And that would open doors for whole new processes and a whole new understanding of them, which it would be another quantum leap, as you say. But of course, we don't know if that's the case.
Well, we've got another gentleman just coming. Let me just do a quick one from our online viewers. What scientific question keeps you up at night? What puzzle do you hope will be solved or hope you will solve during your career?
Yeah, so a puzzle that I hope I will solve during my career would be this question of the proton radius. I mean, is that really a signal of new physics? Is one of the experiments, does that just have a systematic that we don't understand? And this is a key example where I know exactly how to do that calculation. I know exactly what I would do to tell you what the proton radius is from the theory. And then if it agrees with one, maybe that's telling us that new physics is moving the other in the other direction. If it agrees with the other, it tells us something again. Maybe it's right in the middle. Maybe it tells us that both of the experiments have problems. So that's a problem that if someone gives me a big enough computer now or gives me a few $1 million to build a completely custom computer, that's a question I could answer tomorrow. So that's something I want to answer in my career. I guess what keeps me up at night is trying to overcome this exponentially difficult problem of studying larger and larger nuclei. At the moment, without something radical, without quantum computing or these custom computers, we're not going to get there in my career. So trying to come up with something radical to let us get there keeps me up at night.
Can you tell me if any of the 17 basic particles can exist in quantity outside of the proton?
Yeah, sure. So things like photons aren't confined to the proton, right? It's the quarks and gluons are confined, but not just to the proton, to other sorts of particles as well. But, for example, neutrinos, photons, the electrons, they can all exist outside of the proton.
So I guess what I'm trying to get at, too, is in any possibility that quarks, there could be a huge number of quarks creating dark matter that we can't detect because we can't detect quarks by themselves other than in particle accelerators.
Yeah, so the interesting thing about quarks is that they can't actually live on their own. If you take two quarks and you start to pull them further and further apart, eventually what you'll get is they'll come apart, but from the vacuum, quark-antiquark pairs will emerge to give you now two things that are quarks bound together rather than just one. So you can't isolate a quark on its own. It's called confinement. And quarks really can't be dark matter because we know they interact through the strong interaction, and dark matter doesn't.
We have an online question which I think is from a future Phiala. What advice do you have for a high school girl interested in pursuing theoretical physics as a career?
Fantastic. I would say that theoretical physics is built on mathematics, and nowadays it's built on computer science. So at the level of a high school or beginning university student, you need to build those foundations. You need to understand mathematics, pure mathematics as well as applied mathematics. You need to understand computing nowadays. And you need to be able to put all those pieces together when it comes to doing research in fundamental physics.
Any other questions on the floor? Well, please, let's thank very much Dr. Phiala Shanahan.